you to know that you are really special.
Now let's do an example. This is going to be a pretty quick example of how we can take our knowledge of the past of the other three series that I was showing you, the series representations of those functions, the sine x, cosine x, or e to the x. Take any one of those and we can find expansions for other functions as well. So our example will be find the Maclaurin series. So find a Maclaurin series for the following. F of x equals, and we'll have x squared times e to the x. So in this case, we can, it's kind of already written here, but let's think of it like this. So yeah, that's really distinct. But basically, the concept here is that we have something in front times e to the x, right? And we already know that the expansion for e to the x is the following. So we have x squared times e to the x, right? And we can expand e to the x to be 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and I'll just write up to the fourth, 4 factorial, right? Plus dot dot dot, and it keeps going. So what we can do here is just distribute the x squared into each of all of these terms, right? So this is going to be x squared plus x cubed plus x to the fourth over 2 factorial plus x to the fifth over 3 factorial plus x to the sixth over 4 factorial, and so on and so forth. So the way that we can represent this now, and Maclaurin, again, sorry, I didn't mention explicitly, but that's when the center is 0. Sorry, that's a c. When c equals 0. So there's no like x minus blah blah blah. It's just x minus 0. So this is what we have so far. And now we just need to characterize this series. So that would be one way to write this. There's kind of a few different ways to write one series, I guess. And this is like saying x squared times x to the n over n factorial, right? It's kind of like we just took everything in parentheses that you see here. That was the Taylor series expansion for e to the x, remember from the last slide. And we're just multiplying all of the terms by x squared, basically, right? Because that's what we did. We just did x squared times the first term, x squared times the second term, and etc. But another way to write this is just from n equals 0 to infinity, and we can just add the exponents. So x to the n plus 2 over n factorial. Okay? So that's basically it for that problem. And now we'll move on to something else. So now I'd like to go over binomial series. Okay, series. Okay, so binomial series. The first thing where we're going to start here is something called the binomial coefficient. Binomial coefficient. So this is represented by this notation, which is a over n, or I don't even know how to say this. I'll just say this thing. Okay, it's represented by this, which when expanded, it looks like a times a minus 1 times a minus 2 times everything that you need up to a minus n plus 1. Okay, this might look a little confusing, but it'll make sense once we do applications of it. So over n factorial. So here's some examples, first of all. So we have like 6 over 3, let's say. And then we'll do a is 6, right? So we have 6 times 6 minus 1 times 6 minus 2 times whatever, up to, well, okay, hold on. Going back. I'll solve for this term. What's pretty useful is to solve for the last term first to see where you're going to stop. Because if not, you'll just keep going and going, and you don't know where to stop. So let's do 6 minus 3, right? So that would be a minus n plus 1. 6 minus 3 plus 1 is going to be, hold on, I can do this, 4. Okay, there we go. So 4. So we're supposed to stop at 4 on the top, and this is equal to 4. So we're going to stop here. That's 4. Over 3 factorial. So 3 times 2 times 1. So this is going to be 6 times 5 times 4 over 3 times 2. And then those cancel, and we just get 20. Okay, let's do one more, because it's always better to practice. So let's do a little bit more challenging one. We have a fraction now. So this is our a, and that's our n. So let's solve for the end, the final term of the top, right? So we know where to stop. So then we'll do a minus n, which is 3. I'm just going to rewrite that as, hold on, 3. 9 over 3. Okay, plus 1, which would be plus 3 over 3. Okay, and then that's just negative 2 over 3. So we're going to stop at the top. That rhymes. We're going to stop on the top when we reach this value. Okay, so let's start with 4 over 3. That's our a. And then we have 4 over 3 minus 1, which is minus 3 over 3. So this is still positive 1/3. And then we have 4 over 3 minus 2, which is 6 over 3. And here, as you can see, this is going to be our negative 2 over 3. So we're going to stop here. And then we'll move on to the bottom. So we have 3 factorial, which again is 3 times 2 times 1. Okay. So on the top, we're left with 4 over 3 times 1 over 3 times our negative 2 over 3. And then this is all over 6. Okay. So this turns out to be negative 4 over 81, if you do the math. But yeah, that's the general concept behind this notation. And this forms our binomial coefficient. Okay,